So it's pretty straightforward. It's basically if you have something like log base b of a equals c, you can rewrite this as b to the power c equals a, right? That's it. That's the crux of it. Let's see what they got for us. Where did we stop yesterday? I think we stopped somewhere here. We're doing this question, right? Yeah. Let's look at 12. Which kind of brings an important point in physics as well. You see this half-life? This is the time it takes for something to decay to half its weight. For example, if you have some radioactive stuff like radium element, what happens is it loses its mass over time in radiation, okay? Mass can neither be created nor destroyed. So it loses its mass, but it's not being destroyed. It's being converted into radiation or energy, a form of energy. So how does it work? Let's say this guy is 100 grams today, okay? And let's say a week later, it becomes 50 grams. You see, the half-life would be 1 week. And then a week later, it's gonna be 25 grams. Bacteria is usually their population goes up. It's the opposite of half-life. It doubles or something every couple of weeks. But half-life, strictly, it's always gonna be exactly 1/2, okay, after a certain period of time. They've given us an equation. If you look at the equation here, m of t means the final mass. This entire thing, the y there. P means the initial mass. Half is just half. This t means the time that has passed. And this h here at the bottom, this is the time it takes. It's the half-life time. For something like radium, it says its half-life is 1,620 years, okay? Let's look at A. It's what is given in part A. Well, we know the half-life H is 1620. And we know if this one has 5 grams of radium, well, that's going to be our starting weight. P is 5 grams. And we know the time that passes is 150 years. And it's asking us for the Y value. M of T in this case is going to be M of how many years? 150 years. So this is what they're asking us, M of 150. What is the mass of this thing after 150 years? Well, how do we do this? Very simple, plug and chug. So everywhere we see a T, we're going to replace that with 150. So we know P is 5 times 1/2. Well, T is 150. That's the time that has passed. And the half-life is 1620, like that. Do you understand what happened? We listed out what was given, right? And then we're simply going to plug into the equation that is given. Do you want to try plugging that into a calculator? You should get a number that's smaller than 5. If you don't, that means something went wrong. Let me know if you got anything.
I got 5.6.
Okay, type it in like this, because half-life means the weight is always going down. So 5 times bracket open 1 divided by 2 to the power of bracket open 150 divided by 1620.
No, I got 4.6.
That's right, 4.6 grams. So it lost about 0.4 grams of its mass after 150 years. You see that? Now B is going to be the tricky question, because it's not going to be a plug and chug. If you look at B, now what's missing? Let's just write down, well, H is not going to change, right? P is also not going to change. So initial mass is still 5, but now it's telling us the final mass, 4 grams, that's gonna be m of t. The final mass is 4 grams, and what's missing? If you look at, there's 4 letters, right? 4 variables. Which one is missing in part B?
T.
Yeah, t is missing. So now time is missing. We have everything else, yeah? Now this one's gonna be a little bit more difficult, but again, m of t is 4, so we're gonna replace m of t with 4. P is 5 times 1/2. T is missing over 1620, like that. Any ideas on how to solve this exponential equation for t?
You divide by 5.
Yeah, that's right. You would get 4/5 or 0.8. Now what?
Um, do you have to use log?
Maybe. Well, what gave you that impression? When do you use logs? The answer is yes, but how do you know when to use logs and when to not use logs?
When the exponent is unknown.
Yeah. So that's exactly what's happening here. So if the exponent's unknown, what you need to do is you need to take logs on both sides. So you'll get log of 0.8 on the left and log of 1/2 to the power of t over 1620 on the right. Now what?
You bring the exponent down.
Right, so you would get, I'm just going to erase this. So you'll get log of 0.8 equals t over 1620 times log of 1/2. Now what?
Do you multiply by 1620?
Sure. What's log of 8 times 1620? Log of 0.8.
It gives me negative 156.9.
Okay, now what? We're trying to solve for t.
Now you divide.
Yeah, so divide both sides by log of whatever. Log of 0.5 or log of 1/2, and that should give you the final answer, which is t is equals to 521.5 years. Yay. Long time, right? Let's go off on a quick tangent here. Like, what's the point of this, right? Everyone's like, what's the point of this? How old do you think Earth is? Are you a Bible person? I'll tell you what it says in the Bible. It says it's
I'm
around
not a Bible person.
6,000 years old. Would you agree or disagree with that?
No, that's too young. Isn't it probably in like the billions or something?
Yeah, it is. So Big Bang, this is the start of our universe as we know it. This thing happened about 14 billion years ago. Here, I'll give you some notation as well, which you'll probably never use again. It's called GA, which stands for billions of years, which comes from Latin, which says giga annum. It means billions of years. Okay, that's the notation used. Earth is about 4 billion years old. Right, like that. The first life forms that we had, like bacteria or whatever, this was about 500 million years. This is the first life form. And then first humans are about 200,000 years old, I think. This is the, we're not even, you know what we are, right? Humans, right now we're something called Homo sapiens. But there were a different species of people that existed before us. So that happened about 200,000 years old. Now, what's the point of all this? The point of all this is this: how do we know this? How do we know all these years, you see? How could we possibly know these numbers? And that comes from doing something like this. If we have let's say we found a block of radium, right?
Mhm.
We know its half-life, and we can kind of decipher how big that chunk was using technology. So we have P, we have MT, right? And we have H. What's missing is T. Then we solve for T using the same exact formula. So that would be a real life application of this thing, knowing how old really everything is.
Mhm.
This is more for geology though, this stuff. Where this thing really shines is a process called carbon dating. And this is used to use in organic materials. I don't know how to say this without trying to sound mean. It's used to identify how old like a bone or something is. Yeah, that will work. Like dinosaurs, maybe fossils, right? All these we can use carbon dating. It works when it has something has carbon in it. And what has carbon in it? Almost everything. Well, not rocks though. Rocks don't need to have carbon. Not rocks, but something organic, like bones or something. Teeth.
Mhm.
Teeth is good too. We use this method to precisely say how old something is. Like in the news, if you hear, we found a body or something like from decades ago. Well, how do they know how old it is? Well, there you go. They use some very similar thing, carbon dating. Okay, and that would be
Okay.
some real life examples of this exact half-life thingamajig. Is it interesting?
A little.
Now we're gonna look at something called the laws of logs. We had exponential laws before, like a over b over a over c. We subtract them. For multiplying, we add them. Very similar. There are 3 laws. The first one is called, well, I'm gonna call it the product law, where if you have log of a, yeah, the bases have to be the same though. Oh, by the way, if there's no base, so for example, log of 2, if you see something like this means the base is 10. Okay, if the base is 10, we don't need to write the base. That's the default setting on your calculator and everything. So let's say we have some log base of A, and then we're adding this with the same base of something like C. Then what we can do is we can multiply those two. An example would be like log base 3 of 2 plus log base 3 of 8. You simply multiply those two, you'll get log base 3 of 16. This is the product law. And then you have the division law, I guess, which if you remember from exponentials, it's just going to be the subtraction bit. Let's say we have log base b, something like this. They need to have the same base. It's going to be log base b of a over c. An example would be log base 3 of 8 minus log base 3 of 2. It's going to be log base 3 of 8 over 2, 4. Understand that?
Mm-hmm.
If it's plus, you multiply them. So it's kind of the opposite of exponentials, because exponentials, when we multiplied them, we added them up, right? Like that. And we know log is the inverse of exponentials. So it's a similar kind of rule. Like if you add them here, now we multiply them. If we subtract them, well, we divide them. And the last rule is something that we've been seeing already, right? Like if you have log base b of a to the power k, this power comes in the front. You're allowed to bring this power forwards. Like that. Cool?
Uh-huh.
Now using this, what we can do is, let's say we have a big chain of logarithms. We can combine them into one big fat one. What do I mean by this? Here, let's see this. What do we do with this? What do you think? What's the answer? We want to write it as one logarithm. There's two right now, but we can combine them.
You just multiply 4.5 and 6.
Yeah, that's literally what you do. What's 6 times 4.5? 27?
27.
Okay, now what's log base 3 of 27, if you remember from yesterday? 3 to the power of something is 27.
3 to the power of 3.
Yeah, so the answer here, log base 3 of 27, just simply evaluates to 3.
Okay.
Because 3 to the power of 3 is 27. Right? You understand that? I know you do. Okay, B. What do you think the answer to this is? They're being, yeah, go ahead.
Log 2 to the power of 16.
Yeah, what's the answer to this?
Um, 2 to the power of 4.
So what's the answer to this? Is it 2 to the power of 4? Yeah, that's right, 2 to the power of 4 is 16, but what does this evaluate to? Simply a 4.
Okay.
Okay, 2 to the power of 4 is 16. That means log base of 16 is simply a 4. Like log base 3 of 9 is 2, because 3 power 2 is 9, right? Log base, I don't know, like 232 would be 5, because 2 to the power of 5 is 32. We're just strictly interested, the answer will be just the exponent. This one's a little bit tricky. Or is it? You're gonna have to use the power rule, but first you need to convert that cube root into an exponent. If I want to write this as an exponent, what does it become? I want to write this as an exponent here, 25 to the power of. Any ideas? Forget about the log bit, right? Just forget about the log bit completely. We have cube root of 25. If you want to write this in exponential form, has nothing to do with logs, what does that become?
To the power of 1/3.
Right, that's it, right? To the power of 1/3. So like that. Now we are using logs. What can we do with the power 1/3? Think of the power law. What can we do with that? What do we do with the exponents when we have a log? We're using this rule, which is also how we've been solving the exponential equations.
You bring the exponent down and then you divide.
So in this case, 1/3 is just going to come down like that to the same level, right? You understand that bit? The 1/3 is going to
Yes.
drop to the same level because that's one property of log. That's why it's so powerful. If you have something in exponential form, we can just say no thank. Cool.
Mhm.
Now, what's log base 5 of 25? What is this bit? What does that evaluate to?
2.
Yes, so we have 1/3 times 2. What's 1/3 times 2?
2/3.
Yeah, that's it. Final answer, two-step answer if you know what you're doing. Cool. Cool, cool. Now we're going to work backwards. We have this big fat logarithm. We're going to rewrite it as a series of logarithms. Now for the moment, don't worry about the log bit. Just see what the relationship is. We have x cubed, we have y squared, they're being multiplied, right? And then we have a w in there that's being divided. Well, if it's multiplication, we can write that as log x3 plus log y squared. If you have one big log inside which you have a multiplication, what does that mean? That means it's a plus. What about the divide w?
You subtract.
Yeah, you subtract. Okay, keep that in mind. So that's gonna be the goal here. But before we get to do that, you see this big square root? If you want to write this as log base a of x cubed y squared w to the power of something, what is the exponent here? What square? If you have a square root of 3, if I want to write that as an exponent, what is it? One over 2. Okay. It would be 1 over 2. Square root is to the power of 1 over 2. What's next? What's the first thing we do here now? There's 3 laws that we can use, right? The power, the multiplication, the division. What would be the best?
The multiplication.
The multiplication would be the best? Nope. You first need to bring the power down, right? Use BEDMAS. Which one do you do first? You're gonna do exponents before, the E there stands for exponents, right? You're gonna do exponents before you do the multiplication bit, okay?
Okay.
So what you can do is you can pull this guy down here. So it's gonna become 1 over 2 times log base A of x cubed y cubed w. Now what? Here, I'll tell you. I'll do this one. It's going to become 1 over 2. You see we have x cubed, y cubed. Well, that's simply x cubed plus y cubed as individual logarithms. Okay?
Uh-huh.
And what do we do with the w? What do you think? Plus or
You
minus?
subtract.
Yeah, that's it. Minus log a w, and you are done. Final answer. This
Okay.
1 over 2 here applies to everything inside. That's why I put a square bracket here.
Mm-hmm.
Actually, maybe we can go a level deeper. We can go one more level. You see this cubed here? Yeah, I didn't think of that. This cubed and this, you can bring them down. So it's gonna come here. It's gonna come here. And there you go. That's gonna be as far as you can go.
Mm-hmm.
Here, let's try doing this. I don't know if you'll let me. Okay, look at A. We're gonna use the rules if we can. What do you think this is the first thing we do for A? There's no multiple thingies going on. We can't use the plus or the minus rule. What about the cube thing? Can we do anything with that? No?
Could you bring it down?
Yeah, right? You bring the cube down and then you have log 25 of 5. And now here's where's the tricky bit. 25 to the power of something is 5. What is it? It's tricky, right? Well, it's going to be 1 over 2.
0.5?
Yeah, that's right, 0.5. So this entire thing, log 25 of 5, evaluates to 1 over 2 or 0.5. And the answer is going to be 3 over 2.
Mm-hmm.
Good?
Yes.
Okay, tell me for D, what would be the first step? And again, there's just 3 rules, right? You can just toss a 3-sided dice and say one of them, and there's a 33% chance you get it right. What's the first thing we do in D?
You divide.
Okay, yeah, that would work, right? So log base 2, and then you're gonna write this as root 36 over root 72. Yeah. Now what? You can use a little cheat code, which is if you have square root on the top, square root on the bottom, you can write this as one big square root. Okay. So you can write it as log base 2 of square root 36 over 72. What does square root mean in terms of powers?
To the power of 2.
1 over 2. Square root is to the power of 1 over 2. So you can simply rewrite this as 36 over 72 to the power of 1 over 2. Why are we doing this? Well, because we can bring the 1 over 2 down. What's 36 over 72?
1 over 2.
Yeah. Now think about it. 2 to the power of something is 1 over 2. What is it? 2 to the power something is 1 over 2. And it is not 0.5. It's -1. Cool? No? Do you disagree with that? 2 to the power -1 is 1 over 2. So this entire thing, log of base 2, 1 over 2, becomes 1 over 2 times -1, which is -1 over 2, and you are done for the final answer. Let me know if that made sense.
I think it makes sense.
We started with some hocus pocus looking thing. That film just came out, by the way. I don't know if you even know what that is.
I don't know what that is.
Trust me, I don't know either, but the name is catchy. And I know that's a film that just recently came out. It's supposed to be like a children's film, I think. Anyways, let's look at this. Very difficult looking thing, not at all difficult. Plus means we multiply as long as the bases are the same. Divide means, or minus means divide as long as the bases are the same, like that. Right? That is it. Now, 3 goes into this how many times? 1, 18 times. So we have log base 6 of 36. What does this evaluate to? Log base 6 of 36.
Just 6.
No?
2.
2. Done. 1 and done. Easy. This one, same idea. We're adding them. Well, adding just means log base 3. We'll multiply them like this. 2 goes into this how many times? 27 times. 27 times 3 is 81. So we get log base 3 of 81. What does that evaluate to?
9.
Nope. It is not 9. 3 to the power of something is 81. And this something is what it evaluates to. It is not 9. What is it? It's a 4, okay? 3 to the power of 4 is 81, and you're done. 1 and done. Fun, fun, fun. Let's look at C. What can we do with this one? Looks a little bit weird. What do you think? Think about it this way, okay? 6 is just 6 to the power of 1. Square root of 6 is 6 to the power of 1 over 2. Yeah? Now, if you use the exponential rules, what does this become if I want to write it as 1/6? Well, you add them up, right? 1 plus 1 over 2 is 3 over 2. There we go. If you multiply it with the same base in exponential forms, well, you simply add the exponents up. So this becomes log base 6 of 6 to the power of 3 over 2. And we have done this before. Log base 6 and the exponential 6, they are inverses, so they cancel out to 3 over 2. And we're done. Was that difficult?
No.
You just have to be able to see it, right? The math here is very simple. But the little tricks is the issue. Like, you need to be fluidly be able to go from the exponential form use the exponential rules when needed, and use the log rules when needed. Which is why we also did exponents first, because this is the part 2 to that kind of like topic. Okay, this one. You can already see 8 to the power of nothing is 2. 8 to the power of nothing is 2. 8 to the power of nothing is 16. So we can't evaluate this in one step. What we need to do is we need to use the 3 laws. The first one, we can't really do anything with this. Now the second one, you see this 3? We're going to toss it back up there. It's going to become log base 8 of 2 to the power of 3. What about this 1, 2, 1 over 2? We're going to toss it back up there. It's going to become log base 8 of 16 to the power of 1 over 2. Good?
Mm-hmm.
So we have log base 8 of 2 plus log base 8 of, what's 2 cubed?
It's 8.
What about 16 to the power of 1 over 2?
It's also 8.
No, it's not. Try again. 16 to the power of 1 over 2 is not 8. 16 times 1 over 2 is 8, but not to the power of 1 over 2.
Is it
Well,
a 4?
yeah, it's just a 4, right? Power of 1 over 2 just means the square root. Just remember that. Power of 1 over 3 would be a cube root. Power of 2 over 6 would be this thingy is squared inside, but the root is 6. So anyway, 16 to the power of 1 over 2 is just a 4. So we have kind of simplified this to this point. Now what do you think we do?
You multiply everything?
Yeah, you multiply everything. So this becomes log base 8 of 2 times 8 times 4, which is log base 8 of 8 times 4 is 32, times 2 is 64. So what's the final answer?
It's 2.
Yeah, and you are done, right? One and done, easy. Okay, let's try working backwards. So we want to write this as a bunch of different logs, right? Notice we have x squared being multiplied with y squared. So if I want to write them as individual guys, what do I get? They're being multiplied. You get a plus, yeah? Multiplication means plus if you want to split them apart. So you get log base b of x squared, log base b of y cubed. What do you think this evaluates to? Oh, we're just trying to simplify it actually. What can we do with this? It's not going to evaluate anything because it's just a bunch of letters.
Do you bring down the 2?
Yeah, you bring down the 2. So you get 2 log base b of x plus 3 log base b of y, and you are done. That's as far as you can go.
Okay,
Does that make sense or no?
it does.
This one, how do we split them up?
You subtract.
So you get log base b of z minus log base b of xy. Is that the final answer?
Yes.
No, You see xy, we can split that further up because they're two different things here. We can split them apart. It's going to become minus log b of x and then minus log b of y. And that's it.
Okay.
And this one is a minus here because this negative applies to the x as well as the y. So they both end up becoming a negative. All right, what about we try something fun? Which I guess is, where's our whiteboard? Okay, I'm gonna give you a question and you are gonna solve it because you're just that good, I guess. Shouldn't be that bad, to be honest. There you go. We have a bunch of different logs. We want to write them as one. Well, actually, we have one big log. We want to write them as a bunch of different ones. You see this question, right? You want to try and attempt it? Do you see it?
Yes.
You want to try it? It's just the same thing we've been doing all day. Here, I'll give you a hint. The first, rewrite the square root as to the power of 1 over 2, and you can bring that in the front.
And then do I have to put a bracket around everything else?
Mm-hmm, mm-hmm. Lol. Here, this is what you do. This not here, you gotta put it up here. 1 over 2 log x5 y z3, yeah? See, like that? And then what? See, notice how they're all being multiplied. What do you do if they're all being multiplied? Yeah, so you get 1 over 2 bracket open log x5, but then this 5 you can bring it here as well, so it becomes 5 log x plus log well, there's a log b, but whatever, log base b of y plus log base b of z cubed, but you can bring the cubed here in the front, becomes a 3, and that's it. That's the final answer. Good. Well, that was fun. Okay, let me share my screen again. Alrighty. This one's kind of interesting. It says explain why log base 5 of 3 plus log base 5 of 1/3 is equals to 0. Any ideas? I guess not. We have 1/3. If I want to write this as 3 to the power something, what is it? I guess you can write it on the thingy, right? Wait. Here, let me open this thingy again. So the question is, let me put the question on the board. It's basically asking us to prove this. Log base 5 of 3 plus log base 5 of 1/3 equals 0. Now to prove this, we gotta look at this guy. To look at that guy, let's just look at 1/3. If I want to write this as 3 to the power something, what is it? What's in the box? It's in the denominator right now. We want to toss it into the numerator. Anything? Nothing? It would be -1. Which means log base 5 of 3 plus log base 5 of 3 to the power -1 equals 0. And you can bring this -1 out front here. So you get log base 5 of 3 minus log base 5 of 3 equals 0. And we know this is true. That is how we would do this question. Do you see the screen or no? Okay, here's a question for you. Log 1/2 log a of x plus 1/2 log a of y minus 3/4 log a of z. And I want to see the final answer will have this form, log base a of something. I just want this bit. I want it in this form. I want 1 log, not 3 of them. Try it. First thing would be to bring the coefficients that are in the front into the power. And then you can just you can multiply them for the first two and divide the last one. We're trying to write it as 1 log, that's why. Nope. Here, this one would become this, right? Log base a of x to the 1/2. What is the second one gonna be? So the second one doesn't have an x. It has a y. And this, it looks like this, log of subscript a of y, right? Log of subscript a, and then the y is up there to the power of 1/2. What about the last one? It's the same idea. You just throw the coefficient back as the exponent. What does that become? Okay. Now notice the first two, we are multiplying them, right? So log base A of x to the 1 over 2 times y to the 1 over 2. What about the z? Where does that go? The third guy. Where would the z go in this expression? And it is being subtracted. So we've dealt with this one and this one. We want to deal with the z. Right? Z. Any ideas? It's gonna go somewhere in this bracket. That's for sure. By this bracket, I mean this, yeah. Z to the what? And that's it, right? That is literally it, and that's the final answer. You are done. One and done. It's only difficult if we make it, I guess. Let's try another one. Log base 3 of 5th root of 27 over 2187. Look at this thing. It looks super interesting, right? But it's actually pretty easy. What we do is we just split them apart. We know this is being divided, so we will get log base 3 of 5th root of 27 minus log base 3 of 2187. And this square root of 5, or 5th root, is going to come here, because this is 27 5th root, which is the same thing as 27 to the power of 1 over 5. And then because there's a log here, we're allowed to bring it all the way in the front. So we get 1 over 5 times log base 3 of 27 minus log base 3 of 2187. What is log base 3 of 27? Yeah, so we have a 1 over 5 times 3. And then this one we have to check. I think it's 6, but let me double check. 3 to the power of what? 3 to the power of 7 is 2187. That means this entire thing evaluates to a 7. So the answer is 3 over 5 minus 7. Now, what does that equal? So what's 3 over 5 minus 7? How do you subtract these fractions? We're taking away 7 from 3 over 5. So you get 3 over 5 minus 35 over 5. So it's going to be negative 32 over 5. If you write that as a mixed fraction, it's going to be something 5 goes into 32 6 times. The remainder is 2. And there you go. That's going to be the final answer. Okay. We start off with a pretty difficult looking thing, but we can just use the rules to simplify it. And then from there, we can use a calculator or can even use our heads. Anyways, that will be the final question. Yeah, that'll be the final answer to this question. Anyways, let's call it a day there for today.